Welcome to qnawire.
In this question, we have electrons inside a picture tube that will eventually hit the face of that picture tube, producing some photons as a consequence. Then we have to calculate what are the shortest and the longest possible wavelengths that this collision can produce. To do that, we have to use energy conservation, because the energy of the photon, which is equals to h times the frequency of that photon, is equals to the energy the electron had before hitting the face of the picture tube minus the energy that the electrons have after hitting the face of that picture tube. Now, to calculate the shortest wavelength, we have to look for the following. So remembering that the frequency is inversely proportional to the wavelength, we then can see that in order to obtain the shortest possible wavelength, we have to look for the biggest possible frequency. The biggest possible frequency happens when this difference is the biggest one. So, when is this difference the biggest one? It is when k prime is equals to 0. So, the shortest wavelength is obtained by setting hf to be equals to k, which is the energy the electron had before hitting the surface. But in this case, for the shortest wavelength, we are setting k prime to 0, so this electron, after the collision, is now at rest. Then, we get the following. H times f is equals to the energy is equals to E times the voltage, which is 32.5 times 10 to the third volts. So, we get the following value for the wavelength, remembering that lambda times f is equals to c, which is the speed of light. We can relate f and lambda as follows. Lambda is equals to c over f, and on the other hand, f is equals to c over lambda. Then we can write it as h times c divided by lambda is equals to e times 32.5 times 10 to the third. Then, solving for lambda, we get lambda as being equals to h times c divided by e times 32.5 times 10 to the third. Then remember that h is equals to 6.63 times 10 to minus 34 joules times second, and c is equals to 3 times 10 to the 8 meters by second, and finally e is equals to 1.6 times 10 to minus 19 joules by electron volts. Then, by plugging in these values in the equation for lambda, we get that lambda is approximately 0.0383 nanometers, 0.0383 nanometers. Then, for the next item, we have to calculate what is the longest X-ray wavelength that is emitted. Note that k minus k prime can even be equals to 0, which would make the frequency equals to 0. A zero frequency means a very large wavelength, but we want the largest possible X-ray wavelength, and this is of the order of 1 nanometer. So this is the answer.